but we're going to start talking about the interaction of matter and radiation here. And the first thing we'll talk about is the photoelectric effect. And this is basically when electromagnetic radiation is incident upon a metal, it causes electrons to be emitted from that metal. All right. So as an example here is if we had a couple metal plates inside a vacuum container, and these were hooked up to some sort of power source, a battery, and we had ultraviolet light coming in, UV light coming in. I wanted that to be purple, but whatever. This UV light coming in incident upon one of these metal containers, that it would cause little electrons to be knocked off of this piece of metal here, and you'd have little electrons that would then fly across and hit on this other side, and you'd get a little electric current then flowing through this. If this UV light wasn't turned on, then you wouldn't have any electricity flowing through this vacuum, but shining this UV light on there causes electricity to flow. There was a few things that were noticed about this. First, if you increasing the UV intensity, increased the current that flowed, and that should make kind of sense. The more UV light there was, the more current there was. Two, there was no delay. There was no delay. As soon as the UV light was turned on, the electricity would start to flow. In other words, this was a little bit of an indication against the wave nature of electromagnetic radiation, because wave, you'd expect that there'd have to be a ramp up or a build up of energy into this to then start knocking electrons loose. But in fact, there was no delay, so that meant as soon as the UV light was there, electrons were already being knocked off immediately. And the third big thing that was noticed, it didn't work with visible light. So visible light didn't work. So visible light wouldn't work like that, no matter how intense, the visible light was. It just didn't do anything. And so this was kind of a few things that were a bit of a surprise with this experiment. And some of the things that fell out of this from this photoelectric effect was something called the threshold frequency. This comes from the visible light not working, and so what was found was that there was a specific frequency different for different metals and different materials, but it was a certain frequency that above which you got electricity to flow, and below which, no matter how intense it was, nothing would flow. So this threshold frequency was the minimum frequency for the photoelectric effect. So it was a minimum frequency. And this was, again, be sure you remember this, it's independent of intensity. It didn't matter how intense the light was that you used, the electromagnetic radiation that you used. If it was below this minimum frequency, no matter how intense you made it, you couldn't get any electrons to flow. And so this was a bit of a problem, because I didn't quite understand why that would occur. And it took a little doing. Planck came along, and the expectation for blackbody radiation, which we talked about before, so we'll do a little reminder here, classically speaking, we did we've done this graph already before, the intensity versus the wavelength would be expected to look something like this. But if you remember from our blackbody radiation before, it actually looks something more like that. And this was intensity, And so this is what actually happened. This was the experimental result. And so in order to account for this, uh, Planck basically figured out that you would get this shape by quantizing light. And if you quantize light with E equals HF, which you should know already as well, if you quantized light, you would suddenly get a graph that looked like this predicted for black body radiation. And then it was Einstein that came along in 1905, his miracle year, and he realized that this quantization of light that came from this black body radiation solution, he realized this was essentially the thing that would explain the photoelectric effect. So he wrote a paper and explained it using this quantization of light. And so the best example that I think I've ever seen for explaining how this works, why there's a threshold frequency and why it works the way it works is if you had a bucket and you were throwing rocks into it, a bucket full of water and you're throwing rocks. Well, if you have a bunch of small little rocks where each little rock thrown into the bucket can't make a big enough splash to splash the water out of the bucket, well, it doesn't matter how many of these rocks you keep throwing in, right? And the more rocks you throw in, this would correspond to a higher intensity. No matter what you do, you can't get any water to splash out of a bucket. And so that corresponds to this threshold frequency. If you have a little quantized bit of light, which we know is called a photon, and you're sending it onto the metal, and it doesn't have enough energy to knock an electron loose, then it doesn't matter how many you send in, you're not going to get any electrons locked loose. And then if you keep making your little pebbles bigger and bigger, you'll eventually reach a pebble size, right? A pebble size bigger than the smaller ones, that if you throw them in, they actually can just barely splash water over the edge, right? The water would splash, and they can splash some of the water. And this would be basically your threshold frequency. This would be your threshold of rock size, right? And this would be below it. And then anything you go bigger than that, so even just throwing one single rock on, you could get some water to splash out. So sending in one single photon, which would be a really low intensity, could get electricity essentially, get one electron to flow across. And then anything you go above that, you go to higher and higher energy wavelengths or bigger rocks, right? You have these bigger rocks that can splash a lot of water out. Well, then you can get more and more electricity flowing. So this would be above that threshold, and this would be below it, right? So either a single photon coming in has enough energy to knock an electron loose, that would be these examples, or it just does not. And there's a minimum amount of energy needed to actually knock an electron loose, and that would be at your threshold right there. So that corresponds to your threshold frequency for the photoelectric effect. Now, when these electrons are knocked loose, there are going to be some electrons knocked loose. So this is your material here, let's say. So you have your little wavelength come in, and if it hits and knocks an electron free, right? An electron free, this is our UV light, let's say, comes and knocks an electron free from the surface, what will happen is that the energy of the electron, HF, remember E equals HF, has to be equal to the energy, the escape energy of the electron. In other words, how much energy does it take to actually knock the electron loose, then plus the kinetic energy of the electron, right? So remember, this is the photon energy here, the energy of the photon, right? So it has to be equal to that. Well, this stays just HF, but then this escape energy is actually called the work function. Put it with a capital W, and it's the amount of energy it takes to knock an electron basically loose from an atom in that metal. and then this would be plus 1/2 mv squared. All right, and this would be the velocity of it coming from the surface. Well, you also have to think about this is that what happens if this UV light goes in, misses the atoms on the surface, and collides with one further down and knocks this electron loose? Well, in that case, in the case where that occurs, an electron from, so this is from the surface. What happens if it's from inside the material, not on the surface? Well, you still have the energy of the photon. You still have to worry about enough energy to knock the electron loose. The electron will still have some kinetic energy, mv squared, but it will also, the electron will have lost some thermal energy on its way out of the material. So if it's coming from in here, it's going to get close to, collide, get deflected, lose energy to some of the atoms that are in the material itself, and so you'd have this extra thermal energy. So if you look at this velocity here from the surface, this would be the maximum that you'd get, because anything over here from inside is going to be at a lower velocity because part of the energy, this W has to be the same, that's the amount of energy it takes to knock it loose, but part of this kinetic energy is lost as thermal energy, which would reduce this velocity. So we're more interested here in this maximum version here. Okay, so that's the one that we really want to pay attention to, is this version right here. HF equals the work function plus 1/2 mv squared maximum. Now, in addition to this experiment can be done where you take your little vacuum tube, right? I'm not going to draw it, well, actually I probably should draw it as big as I did before. All right, let's erase that. Let's make this bigger. So let's take our little vacuum tube here, and we're going to send electrons off of here. This time I will actually get some purple or something here. So UV light, ultraviolet, right, comes in, UV, and then little electrons are going to get knocked loose. And these electrons are going to go flowing right across here. And what we want to do is, before we had it set up where this was the negative side, this is positive, we want to flip that around. We basically want to apply a voltage in the opposite direction. And in other words, the electrons are going to try and get knocked off of here, and they're going to want to just, they tend to want to go this way. But what we're going to do is apply a stopping potential. It's called a voltage in the opposite direction. This is our stopping potential or stopping voltage. Okay? It's our stopping potential in volts, V sub S. And we're going to apply that there. And what you're going to do is slowly ramp this up higher and higher. Slowly ramp this voltage up higher and higher. Because at first you start off with it maybe at 0 or pointed in the other direction. And you're going to get electrons that are going to be able to make the jump across and flow. But as you start to ramp this up, what will happen is you'll start to reduce the current. Because the low energy electrons, they're going to get turned back around. And they're going to be pushed back this other way. And if you keep ramping it up, what will happen is more and more of these electrons are going to get turned around. And eventually what will happen is you'll get the high energy ones. Those high energy electrons will start to be turned around. And so you want to ramp this up real slowly, making this side the positive side now and this side the negative side, until you completely stop the current, until you just stop the current, right? You just stop it. And as soon as you just stop it, that's when this becomes this stopping potential, this stopping voltage. It's basically the minimum voltage you need to stop all of this current flowing from this photoelectric effect. And if we look at it, we can rewrite our equation from above up here. This time it's HF equals W, the work function, we need to get off it, plus, well, the kinetic energy of the electrons, whatever energy it took to just stop them, to reduce their energy and totally stop their motion, to just stop it, is simply the charge times that potential that you're applying. Because remember, voltage is potential energy per unit charge, so the charge of an electron times the potential we applied would then be the potential energy we needed to stop it, or the amount of work we had to do to stop it, which would have to be equal to the kinetic energy that the electron had, right? So this EV, right, a little off to the side, EVS is equal to that 1/2 mv squared max, okay? That's basically what we have going on here, right, this little thing. And if you look at this, this is a nice, just doing a little rearranging, we can rearrange this as EV stopping is equal to, right, HF minus W. And if you look at that, this is a linear equation. This would be Y, this would be M, this would be X, and this would be plus B, right? So if we go and actually graph this, you can graph this with EV here, stopping, graph that, and do then frequency over here. What you'll get is a nice linear relationship, right? The slope of this, the slope will be H, that's what it corresponds to here, right? Our independent variable, of course, is F. Our dependent variable, Y, is EV. And then our y-intercept would be negative of the work function, so negative W. That's our y-intercept. And then the part here where it crosses, that would be when the stopping potential is 0. In other words, where you don't need this stopping potential to do anything. That's basically going to be your threshold frequency, because at that point, with that frequency, nothing had to be applied, and so that's our threshold frequency there. Okay, so what you're going to do is you would do this experiment, you would vary the frequency of light up, right? And you're probably only going to get this part because below here you're not going to actually get any voltage, any current flowing. So you start here and you start ramping it up, and you get some linear set of points in here, right? Some linear set of points in here. You do your line of best fit as you go through these different frequencies and finding all the stopping potentials, right? Because this has to be, so you'd start with whatever frequency was, you'd measure its stopping potential, you put a point. Go to a higher frequency, measure the stopping potential by varying this voltage here, get your second point, then your third point, then your fourth point. Keep doing higher frequencies, finding the stopping potentials, plot them out, do a line of best fit. Where it crosses the x-axis, that's going to tell you what your actual threshold frequency would be, and then where it actually hits the y-axis would then tell you what the work function is of the material. So you can do this to figure it out. If you're looking at this little equation here, you may have noticed, and I'll do it off to this side, that you could have written this as Vs is equal to h over E times frequency minus work function over the charge of electron. And if you did it this way, it's still a y equals mx plus b, and you can still graph it, right? So you still get some graph, some linear graph. It's just that now the slope is equal to h over E, not just h, and this still crosses at f naught, and of course this is still frequency, and this now is stopping potential purely, not your stopping potential energy, not EV. And then down here where it crosses is still, instead of just being minus W, it's minus W over E, minus the work function over E. So sometimes you might see it graphed this way, but either way, it's still just that linear function. It's just that you divided that charge of an electron over to do, just to make it in, I don't know if it's a slightly better form, but just into a slightly different form. So the last thing we have to talk about for this is the saturation current. So what will happen is eventually, if you keep applying more and more of this to this, you're going to reach a point where the amount of current you're getting from this is going to max out. It's going to plateau. So if we're doing this above the above our little fundamental frequency, our threshold frequency, right? Because if we were below it, we wouldn't get anything. So what we can have here is the amount of current produced as a function of the voltage that you apply, right? Now back down here, over here, you would have the stopping potential, the negative of the stopping potential there. That would be when we had zero current, so that's exactly what that would be. And then as you started to move that voltage up, the current would start to increase. It'd be a little bit at first, and it would just increase and increase and increase and increase. And then when the voltage was now pointed in the direction that it would help the electrons, you can get this thing to go up some, but eventually what will happen is it'll turn over and it'll plateau. And this plateau is your saturation current. This is your saturation current right there. Okay? That's your saturation current. Sorry, I got those so close together. But this plateau where there's more light coming in, but electrons can't be knocked off any further, and this voltage isn't help pulling them out. But for whatever current light you're shining on it and current intensity you're shining on it, this is the maximum electrons that you're going to be able to get out of it, and turning the voltage over any higher isn't going to help you get any more. So if you were to do this for different wavelengths of light, different colors of light, and you did this at the same intensity, so we'll do this same graph again, right? Still V here, current here. And if you did this for, again, if you do this for a couple of things with the same intensity, so two different wavelengths, so two or many different wavelengths of light being shined onto this. If you keep it at the same intensity, then the one with the higher frequency, in other words, the shorter wavelength, so the higher frequency, the higher energy ones, the higher energy photons, well, basically you're going to need a smaller number of photons. The higher energy photons, to get the same intensity, you need less photons. So higher energy photons means less photons, because there's more energy per photon being carried. So if you need 10 photons to get a certain frequency or a certain intensity of the lower energy light, you might only need 6 of them to get the same amount of energy for the higher energy photons. And less photons means the less photons being there means a lower, less photons basically means a lower saturation current, because only one photon can knock one electron loose, and so if you have less photons coming in, you can knock less or fewer electrons loose. So if you were doing that, your graph for, say, like red light would have a stopping potential like back here, right? And it would look something like, like this, and come up and plateau, right? But then blue light, right, let's go with blue, it would have to have a higher or a larger in magnitude stopping potential, but then it would saturate. It would saturate over at a lower saturation than the red light would, because there are fewer photons in this blue light at the same intensity as this red light. Now keep in mind, the big part of making this graph is it has to be these two things, or 3 or 4 things, and they have to be at the same intensity. If they're not at the same intensity, then you can't necessarily say what the stopping potentials comparison would be without knowing how much more intense one was than the other. You have to go through and do more calculations of this. So it will be lower for the higher frequency lights if they're at the same intensity. So hold them at the same intensity. The high energy photons, you'll have less of them to get that same amount of energy, because each photon has more energy per photon. And so if you have less photons, you can knock less electrons loose, which means you have a lower saturation. Okay, that's all that there was for this first part. and we'll continue on in another one.